So we've started working with inequalities, and we've found that these inequalities often have infinitely many solutions, but not all of the real numbers. It's usually just part of the real number line, and we use a number line graph to represent that. But the inequalities we've studied so far are pretty basic. We've done things like x is greater than 17, and we've represented those solutions on a number line, which is a horizontal line with arrows at each end. It has tick marks on it, and those tick marks are labeled with a scale. I like to put the boundary number right in the middle if I can, and then number these ticks accordingly. Remember, the numbers toward the negative side go left and the numbers toward the positive side go right. And then what we do to graph this is we look at the inequality symbol. Since this is just a greater than sign, we mark that boundary with an open circle. 17 is not greater than 17, so we can't circle it in, but we can mark it with an open circle. And then all these other values that are bigger than 17, they are part of the solution set. So we graph them by shading those points. And it includes all of the integers, all the whole numbers, and all of the fractions and decimals and irrational numbers that are included on this side of the number line. Now, it's not all the real numbers because we're missing these guys on the left. But this graph, this picture, represents this inequality, that the solutions are all the numbers that are bigger than 17. Keep in mind that our circle is big and it's directly on the number line, and our shaded arrow is big, borderline obnoxious, and directly on the number line. Now, inequalities that have this form aren't very interesting, and so we're going to start solving inequalities that require adding or subtracting to find the solution. The good news is you already have the tools in place to do this because you've studied equations, solving equations in Chapter 2. And so we're going to use the same inverse operations that we used before. This is going to feel very familiar. The only real new thing is these number line graphs that you have to draw to represent the solutions. So let's jump right in and give it a go. So let's start with the inequality x plus 9 is less than 15. Of course, you could start guessing and checking and trying to plug different numbers in for x until you figured out what the solutions look like, but that's typically inefficient. Instead, what we can do is we can use what we learned in our other unit on solving equations to help us zero in on this solution. Keep in mind that this inequality symbol splits this statement into two sides, just like the equation split the statement into two sides. Now these aren't balanced because this side over here, the left side, is always less than the right side, which is 15. But as long as we keep that inequality intact, we can do some things. Turns out if you have an inequality and you subtract 9 from both sides, the inequality still holds true. So we can use these inverse operations, just like we did with equations, and we still have a true inequality when we're done. These 9's turn into 0, and we end up with x is less than 15 minus 9 is 6. And now we're down to an inequality that looks a lot like what we worked with on the last slide, right? X is less than 6. Any number that's less than 6 makes this inequality true. We could plug any number less than 6 in for x, add 9 to it, and it would be less than 15. Now, there's an infinite number of those solutions, so we don't list them all. Instead, we draw them on a number line. So I make a horizontal line as straight as I can, evenly spaced tick marks to represent my scale. My boundary is 6, and I'm going to do my best to place that as close to the middle as I can, and I number it accordingly, 6, 7, 8, 9, 10 to the right. 5, 4, 3, 2, and so on to the left. Remember, this is the negative end. This is the positive end. And then I want to go ahead and draw my solution. X is less than 6. Again, we look at this symbol here. There's no equal sign underneath it, so 6 is not one of the solutions, but it's my boundary, so I put an open circle there. And then this is a less than symbol, so all of the numbers less than 6 are solutions. That's 5, 4, 3, 2, and so on. All of these numbers. And then I make it almost obnoxious, right? It's borderline obnoxious, and I shade it in so there's no question that this is the side of the number line that contains all the solutions. Circle is open because 6 isn't included, but all the numbers less than 6 are. So that's our solution. We have a inequality statement, x is less than 6, and we have a number line graph representing that. The key to this problem was inverse operations. When you see a plus 9, our inverse operation is minus 9, and we go ahead and do the things that we learned before. Let's try another one. Here we have the inequality D minus 3 is greater than or equal to negative 6. Now, just like our other inequality, that greater than or equal sign is sort of the divider between these two sides. The left side is always going to be greater than or equal to the right side. And just like before, we're going to use inverse operations to isolate this variable. We're still trying to isolate the variable. It just happens to be an inequality instead of an equation. Okay, so the inverse operation for minus 3 is plus 3. We have to do it on both sides if we want to maintain the inequality. You can't just go adding 3 to one side. It changes things. When we do that, these cancel. So I'm left with D, which is what I wanted. I wanted to isolate D. And that's going to be greater than or equal to whatever negative 6 plus 3 is. Careful with this one. Remember, this is negative 6 plus 3. Quick calculation, that tells me that this is negative 3. So my solution is D is greater than or equal to negative 3. There are an infinite number of those solutions, so I can't list them all, but I can draw a picture of it on a number line. Horizontal line, evenly spaced tick marks. I'm going to put negative 3 in the middle. Now, be very careful how you're numbering this. Remember, the positive numbers are this way. So that means I got to count towards 0 here. So negative 3, negative 2, negative 1, 0, and then the positive numbers are after that. That means this is negative 4, negative 5, negative 6, negative 7, and so on. I'm going to shade this one in green just for kicks. Okay, now this is a greater than or equal to symbol, and the boundary is negative 3. So this time, because that equal sign is involved, we go ahead and we shade in our circle and make it a dot, a big obnoxious green dot. Our solution is all the numbers that are greater than or equal to negative 3. That means it's the numbers on the positive side. So we're going to shade this direction. Make a big obnoxious arrow there and shade over the number line so it's obvious that these are all the solutions to this inequality. 0 works, 100 works, negative 1 works, even negative 3 works in this case. That's why the dot is solid. Okay. And that's about all there is to this. We have an inverse operation, which is either going to be plus or minus today. And then once we get the inequality, we make sure we draw the correct picture for it. Let's try one more. Okay, now I know what you're thinking. There's decimals here, and that sends a little bit of a chill down everybody's spine, but you don't need to panic. This problem is going to be very doable. Remember that green line there, that's our dividing line. And remember, our goal is to isolate this variable. The variable's n. Right now, n happens to be on the wrong side of the dividing line, right? When we solve this inequality, we want to end up with either n is greater than, or n is less than, or n is equal to some value. And so you know what I like to do in these cases is I like to switch this whole thing around. Now, there's one extra step to switching this when you're doing inequalities. Not only do you change the position of the n minus 0.4 and the 0.7, but in order for this to remain true, we have to also flip that symbol around. So that the tip of the greater than or the less than or equal to points towards the n minus 0.4, just like it did up here. See how this tip points there? Well, we need this one pointing here. All right? So when you flip this thing around to get that variable on the left side, also flip your inequality around. Okay, now we're in a situation where we've still got our dividing line here, and we need inverse operations. We're trying to isolate n, so we're going to add 0.4 to both sides. Don't worry about what that equals right now. If you can't handle it, you can always have your calculator help you. The 0.4 is on this side, cross out to 0, and I isolate my variable n on the left. It's going to be less than or equal to whatever 0.7 plus 0.4 is. Quick calculation tells me that's 1.1. Now, all the solutions are the numbers that are less than or equal to 1.1. There are still an infinite number of them, so we're still going to draw a picture of this thing on the number line. And I don't want you to panic, but I also want you to think this through. Remember, we're putting evenly spaced tick marks on this number line, but I don't want to count by decimals, right? I want to count by integers usually. And so I'm going to just put 0, 1, 2, 3, 4, 5 this way, and then -1, -2, -3 this way. And then I'm just going to make a little note that 1.1 is just past 1. It's between 1 and 2 on the number line. It's closer to 1 than it is 2, but I'm not going to worry about exactly where it belongs. That's the place where I'll mark my boundary number. So even though it's not right on one of my tick marks, I can put in the little extra tick mark for 1.1 just to indicate it, and then that's where I'm going to put the big obnoxious green circle. I'm going to fill that circle in because of this little equal sign right there. And then our solutions are everything less than or equal to 1.1. And less than goes to the left. I shade this in so it's borderline obnoxious. Right? That way it's clear which side of the number line I'm shading. We make this a big deal because oftentimes we see students who barely, if at all, even indicate that they're shading in one side or the other. So I make a big deal about it, and I want you to be borderline obnoxious when you draw those in. So the solutions in this case are all the numbers less than or equal to 1.1, and this picture describes that. Okay, now let's do some word problems. Okay, you're going to be dealing with some story problems, word problems, and we're going to use inequalities to help us answer these questions. This one is sort of a flashback, and you'll see when I read the statement in a minute here how funny this is, but the memory in Tania's camera phone allows her to take up to 20 pictures. I know 20 pictures is a huge amount for you guys. I can't believe there were ever phones that would actually take 20 pictures, but there were. Tania's already taken 16 pictures. What we're asked to do is write, solve, and graph an inequality to show how many more pictures she could take. Okay. So let's think about this. She's already taken 16 pictures. She can take up to 20, which means we're going to be adding on a certain number of pictures. Now, what does this words up to? What do the words up to mean? That's going to be the most important thing we translate right there is the up to. The equation, or the inequality is not really that bad. 16 plus however many pictures she's going to take. I'm just going to call that P. And then I just need some symbol, and then I'm going to have a 20 here. Well, up to 20 means I could take less than 20, or I could equal 20, but I'm never going to go over 20. So that's a less than or equal to symbol. Once you get the inequality written, you're done with the first part, which is you wrote the inequality. To solve the inequality, we'll use our usual inverse operations. The 16s are gone. This is P is less than or equal to 20 minus 16 is 4. So we've isolated the variable, and we've discovered that Tania could take less than or equal to 4 pictures. Now we've got to be a little smarter with these story problems than we are with the inequalities where there's no context. Because there are certain numbers that make no sense in this problem. Notice I'm numbering this right now as I speak. Okay, here's the problem. When we shade these arrows for our solutions, we do that because all of the numbers either greater or less than work, and we're talking about real numbers here. So things like fractions, decimals, negatives, those make sense when there's no context. This particular problem, some of those numbers won't make sense for us. There's really only a certain number of photos she could take. She could take 4, right? If we are less than or equal to 4, she could take 4. So I'm going to put a dot on 4. But we don't want to shade everything less than 4 because she can't take 3.5 pictures. She could take 3, so I'll put a dot on 3. But we still don't want to shade everything else because she can't take 2.5 pictures or any other decimal or fraction there. She could take 2. She could take 1. She could even take 0. But there's no way for her to take any other values on this number line. She can't take negative pictures. There's no such thing as negative pictures. I suppose you could argue that she could delete pictures, but that's not really part of the context of this problem. We're just asking how many more pictures could she take. So she's not deleting them. And so as it turns out, this particular graph only has 5 dots. She could take 0, she could take 1, she could take 2, she could take 3, she could take 4. She's not going to be able to, we're not going to be able to shade this whole thing in because she can't do the negatives and she can't do the fractions. Cameras don't work that way. So that's a subtle yet important aspect to some of these story problems. This is called a discrete graph actually, because we can't shade everything. We don't use the fractions. I'm just going to add that word here in case we need it later. All right. A discrete graph is where the solutions are just whole numbers or integers, and we just place dots on the graph instead of an arrow. Keep an eye out for that when you work on these problems. Let's take a look at one last word problem, and then I'll get out of your way. Okay, so this is more like a number statement than it is an actual story. But we have to convert this thing into an inequality and then solve it. It says 10 less than a number is greater than 42. And there's 2 things that are weird here. I see the phrase less than, and I see a number. But then here, we see is greater than. So that can be a little confusing to students the first time they work with that. So let's break this into pieces. Is an important word for us. That's a verb there. So I'm going to kind of split this into 2 parts. Okay. This first part says 10 less than a number, and we've seen that before. The part that we see where it says a number, we typically call that a variable, like x or n. And when you want to do 10 less than that number, remember that means subtracting off from that number on the right side. So the first part of this sentence, 10 less than a number, we're going to write as x, minus 10. Then this part I have underlined in green where it says is greater than is the actual greater than symbol. And then since it is greater than 42, that's the last piece. We stick the 42 on the end. So this less than right here is actually a subtraction. This is greater than right here. That's the inequality symbol. So keep an eye out for that word is. Once you get it written down, you're back to business. X minus 10, we're just going to use inverse operations. We do plus 10 on both sides of the inequality symbol. Don't forget your dividing line, right? That inequality symbol sort of splits this into two sides. And we're allowed to add the same thing on either side, and it maintains the inequality. These 10s cancel out. I isolate the variable x. And what is this, 52? So I wrote the inequality, I solved it, and I'm going to now graph the solutions. We need a number line graph. And I'm going to put my tick marks, but I'm not going to worry about the fact that this number is 52. I'm just going to do what we've done before. I'll stick 52 close to the middle and keep numbering. 53, 54, all the higher numbers go this way. 55, 56, 57. Now, behind that, or to the left of that, I've got 51, 50, 49, 48. Okay? So we've got our number line, and then this is a greater than symbol. I do not shade the circle in. I just make it an open circle. And the numbers that are greater than 52 are things like 53, 54, 55, and so on. So I'm going to shade in an almost obnoxious fashion this side of the number line. Make it thick so that it's obvious which way you're shading. And I say that because most of you don't do your homework in multicolored ink, right? You're using a pencil or a pen that is all the same color. And the only way for me to see that you're shading one side or the other is if you make it thicker. This side is obviously thicker than this side, and this is where all the solutions are over here. Okay? All right, now here's one other thing I want you to notice. As long as your variable is on the left side, your inequality symbol will always point the same direction as the arrow that you shade. Go back and look at the other problems that we did, and that was always the case. When the variable was on the left, this symbol right here pointed in the same direction as the arrow that we ended up drawing. This one points to the right. That's just a little trick so you can check yourself. Okay, good luck with solving these. These are just one-step addition, subtraction type inequalities. They take one inverse operation, and then you go ahead and draw your graph to graph your solutions. Be careful with those discrete situations where we're not talking about real numbers, where we're just placing dots down like the last story. And, have a little fun with this. Get it done and move on to the next lesson. Good luck. See ya.